Okay, so for my session today, I'll be discussing deep dive into ORAN architecture. It really is a deep dive because we're going into the detail of the architecture itself, how it relates to the traditional RAN, and then how ORAN or Open RAN is different from the traditional radio access network architecture. Okay, so actually these slides here are also the course content, no, in if you're one of the partner universities in Iora, we also offer this as part of the course. So you'll notice that this is the outline for that. No? After the course, we expect the learners to be able to summarize the evolution of the RAN architecture and define various types of RAN, particularly depending on their deployment, how, like as mentioned in the Kahoot, how the DU, how the BBU or RU are placed, and things like that, which we will cover later. Don't worry about it. Okay, and then much later in this slides or in this discussion, we'll go into the types of hardware or the components, the interfaces of the ORAN architecture. So there are a lot of acronyms here, but by if you're always exposed to these types of content, then you'll be able to really get a good grasp of this content. Okay. So these are the topics that I'll cover. Since we only have 1 hour, um, I hope that I'll be able to cover all of them. But if not, it's okay. I hope that you will be able to join the IORA Academy soon. Okay, so first we'll just cover RAN architecture evolution. A lot of this content was also discussed last week by Richard. And I hope that you will be able to remember a lot of the content here. And then this is important so that we can establish why there's a need for the Open RAN architecture and how is it different from the current architecture that we have now. And then later we'll be able to see the architecture. You may have noticed that in Kahoot, there was an image when the question was about the types of interfaces. And there were lines, there were some blocks. We'll be able to cover them later. And then how does ORAN complement other standards? For example, 3GPP or the third generation partnership project, which is the organization in charge of the management, or rather the maintenance of the technologies relating to 3G and onwards. Actually, even the 2G, they only started with the third generation. That's why they're called 3GPP. And then let's look at what the functions, the nodes, the interfaces defined by 3GPP and defined by ORAN Alliance, and other relevant interfaces that may be utilized. And later, some implementation options and deployment scenarios. Okay, so majority of the content here are really more on the theoretical side, and hopefully this will be augmented later by our industry speaker. Okay, so first of all, let's have a review of the radio access network, particularly in the context of Philippines. You may remember a figure similar to this one on the left in the previous discussion or the previous week's webinar, wherein there are some mobile network coverage depending on the technology. We have 2G, 3G, 4G, 4G plus, and 5G. Okay, so sometimes there are some generations that are in between the integer numbers, like this one 4G plus, because the rollout of the cellular technology is usually in phases. So there are some initial phase and then next phase and so on. So if you're interested to know more about the different phases of the cellular technology, you may go to the 3GPP website, and then there are a lot of content there, and there are white papers on this and things like that. But in general, for each generation, there are significant mm, technologies there. When 2G was introduced, it was focused really on digitizing the voice. We did not include 1G because there's no 1G anymore. But 1G is the first cellular generation wherein it really is just analog voice. So everyone when you say analog, if you're an electronics engineer, you're already familiar with the analog communications. But if you're not, it just means that there's the signal that is being transferred is not digitized, it's continuous in nature. And in that case, there were some security issues there because if the signal is analog, anyone can just tap in, or rather tap in the same frequency and hear the conversation. So there was a security issue there. And eventually, when we entered 2G, it's now digitized. They were able to incorporate some encryption to ensure that not everyone can easily tap into the conversation. And also, particularly in Philippines, we're mostly the use of SMS, or the short messaging service, or just the text became popular because maybe the operators realized that, oh, this will be quite famous in the Philippines, and until now we're still using this. So yes, even though we're already in 5G, there are still some 2G base stations because of the use of text messaging in a lot of applications, from OTP, from updates and things like that. Okay, and then later, 3G came, and the focus of 3G was more on mobile data and be able to stream a bit of videos. No, not as fast as other generation of technologies. And then 4G came. It focused on mobile broadband, which made maybe taking Zoom or joining Zoom a bit better. And then 5G is there are three major technologies under 5G. We have EMBB, enhanced mobile broadband. So it's mobile broadband, but it is enhanced. And then we have ultra reliable low latency communications, and MMTC is massive machine type communications. Okay. So if you're curious to see what's the current radio access network coverage in your area, you can go to this website. So maybe I can copy it and then I'll paste it on the chat box. Okay. Yeah. And so maybe I can also share my screen so that you can see it. Okay. So if you go to this website, of course you should choose Philippines so that you can see if you're in the Philippines, and then choose your mobile operator. So any operator. No, I'm not endorsing anyone, but maybe I'll try Smart for now. Last time when I presented this, I used Globe. So you'll notice that there are some um, colors here because they indicate the different types of the mobile network. Let me just zoom in. Yes, yeah. Okay, so notice that the cellular generations are here. And also take note that when they gathered this data, I think this was less updated recently. Okay, so when they gathered this data, they went through a drive test. So they were in maybe inside their cars. The engineers were inside their cars, and then they checked the availability of the cellular generations. So you notice that maybe some parts that are not in the major highways, there are no data. But that doesn't mean that there are no coverage there. The It's just that when they gather the data, they just consider it a point. So when the engineers design this, of course they have they usually follow a honeycomb pattern, wherein the coverage, the different geographical locations should be covered by certain base stations. Yeah, but anyway, you notice that in this is around Metro Manila, there are 5G connections already, and then 4G plus, and maybe if we go to somewhere else, yes, maybe in some places, no, it's not as deployed yet or not as strong yet. No? There's only 3G in this case, and maybe in other far-flung areas, maybe in the community areas, they only have 2G. So there is the reason for this, of course, maybe they don't have the base stations yet or the radio access network yet or the RAN. And of course, setting up a new RAN would have corresponding cost, especially if they need to set up another generation that would entail a new set of costs, a new capex or new capital expenses. And so I hope you were able to try out this website, this special feature here. Check whether maybe if you're going to travel, you're going to travel somewhere else, you can check. Do they have 4G there? Do they have 5G there? Maybe this is one way to to see if you can access the internet while on the go. Okay, so let me go back to my presentation. Yes. Okay, so these are just some pictures or some screen capture of that website. You can see that in different major cities in the Philippines, mostly it's 4G and 5G now, or specifically 4G plus and 5G. I think maybe this data may already be outdated because, as you have noticed, there are newer updates. So I hope that there are a lot more radio access networks here. Okay, so there are thousands of radio access networks just in Philippines, and imagine if they have a lot of equipment, no, a lot of hardware, and the challenge is to deploy them and then of course maintain them. So what are the typical equipment that we can see? So in the telecommunication systems, usually we can separate the different parts into the core network, the transport network, and the access network. Okay, so the core network here, of course, this one is the core of the telecommunication system, wherein it is interconnecting different parts or maybe different service providers as well. And that's also beyond the scope of our course because usually we're just focused on the access network. And then to connect the core network to the access network or vice versa, we have the transport network. And then the access network or the radio access network or RAN is the one providing the radio coverage or the RF to the user equipment or your mobile phones, to your gadgets, any device that has a working cellular card or net cellular network interface card. So you may notice that this radio access networks look like this. It depends on of course, where it is located. There are some antennas there, and usually, they serve a certain area of the geographical location. Okay. So we're going to focus more on the access network side. No? That's why it's RAN. Okay, so in the different generations, the like 2G, 3G, 4G, and 5G, there are different types of RAN, and the terminology usually varies. No? The naming, like as you can see here for 2G, the 2G technologies, some 2G technologies are GSM and Edge. You may have noticed this on your phones. So when maybe some of your phones will still show 2G, they will show GSM or sometimes Edge. No? And then the radio access networks for this would be this GERAN or GSM Edge RAN. So GSM is 2G and Edge is more on 2.5G. Okay, they also have some major components like base station controller and then the base transceiver station. Or yeah, that's why we call it the base station. And then for 3G, it's no longer called like a base station, but rather it's called differently. We call it UTRAN or Universal Terrestrial RAN. No? This 3G is UMTS, Universal Mobile Telecommunication System. Okay, and then they also have these important components called the radio network controller and the node B. So node B, if you hear node B, that means it's a 3G radio access network. Okay, and then for 4G, another set of the different name. We have EUTRAN or Evolved UTRAN. And then the base, or rather the RAN, is the eNode B. So later in the architecture, you may find that there's an eNode B here. So that means it's 4G. And then for 5G, we have NR or the new radio or the 5G RAN. And then the particular node is called as G node B. Okay, so why do we need to know this different RAN? Because of course, if you're in the industry, you need to know what cellular technology you're going to use or your company has, so that you know how to handle any deployment scenario and things like that. No? So notice there are different implementations. So if the telco only has maybe 3G, they have to really deploy another set for 4G. And currently in Philippines, the 5G scenario is non-standalone. It was mentioned also in the Kahoot. We have the standalone and non-standalone. When you say non-standalone, it still relies on the 4G core network. It's not yet standalone. It's not yet separated. So right now it's in NSP. Okay, so that's the different RAN generations. Now, if you're curious when this was deployed, of course 5G was deployed in 2020, and then 4G 2010, then 3G in 2000s, 2G 1990. So you can infer that every 10 years there will be a new set of generations. So eventually there will be 6G as well, but that would be expected around 2030. So right now we're still in 5G. The different phases of 5G is still being rolled out. And as I mentioned, no, it's not a abrupt change. Usually there are phases in place. Okay, so just to give you an overview of the LTE network architecture. So when you say LTE or long-term evolution, this is a 4G network or 4G cellular network. So they have this one is the end user, and then this is the what we call the remote radio head, and then the E node B, which is I mentioned earlier, no? And this is the RAN, and then we have this is the RAN. This is the front hall interface or FH, and then you can connect to another E node B, so maybe place somewhere else geographically. And then this is the interface now to interconnect the different nodes. Okay, it's the X2 interface. And then the S1 interface is more on the transport or the backhaul interface to the core network. So essentially, this part is the RAN, the red ones. Then this is the core. So just like what I have discussed earlier, you still just have the core, the transport, and the access network. So the main differences, of course, would be the names of the components, and then their application, the type of interface that they use, and maybe the capacity, how fast how fast the speed can be, and things like that. And then for 5G, we have the two general types. We have the non-standalone and the standalone networks. So when I say non-standalone, the 5G RAN would rely on the 4G core network. So as you can see on the left, we have the non-standalone case. We're in the radio access network, this one, may have E node Bs for 4G, and then we also have G node Bs for 5G. And then both of them are connected to the EPC or the evolved packet core in this case. And then this is the 4G core network. Okay, so non-standalone, meaning it's still relying on the 4G. And then for the standalone, it no longer relies on the 4G core network, but it's now by itself, the standalone, and it uses different interfaces. Like as you can see here, it's now XN, and this one is next generation control and user plane and things like that. Now, so usually it's not an abrupt change. Okay, so that's like a review, you know, of the radio access networks. Let's now look at how the RAN has evolved beyond just the 2G, 3G, 4G, and 5G. We'll look at the different components, you know, the what I mentioned earlier, the remote radio head, and the other components. Okay, so what is the reason for a lot of the evolution, particularly towards Open RAN? It's mostly because of the separation of the hardware and software. No? So right now, because of the virtualization, there are a lot more technology that can be virtualized and can be run on a commercial off-the-shelf circuit. Okay, so remember the diagram earlier, we have the core network, the transport network, and the RAN. So in this case, the within each part, now we can disaggregate it into smaller subsystems. And then disaggregation just means the separation of the hardware and the software. So that what does it mean? It means that the the function is not dependent on a particular device. So maybe in the past, if you buy a certain baseband unit, it's just the baseband unit. No, you can't use it for other things. No, but with the disaggregation and virtualization, you may have your traditional commercial off the shelf, like COTS server, and then you can just put in your virtualized functions like virtualized core network, virtualized RAN to be able to operate it on the same device. The advantages, of course, of virtualization is that if you need to upgrade something, you don't need to buy a new hardware for that function. You can just maybe um, install a new one, deploy a new one on the same hardware, or maybe upgrade that hardware that can still be used for other applications. Okay. So for Open RAN, we focus on the disaggregation of the radio access networks, which were originally they have their specific functions for each device, and the only function for that goal. No, but now we can have them virtualized. That's why in the previous webinars, now if you were able to attend, there are discussions on virtualization and AI because it will be a part no, of the Open RAN. Okay. So the evolution of the hardware and software disaggregation did not just start with Open RAN. This has been part of the evolution of various computer devices, computer um, hardware, mainly from the servers. No? Maybe the servers before were um, just really specific. They have a specific function, but as technology progresses, the cost of the computers, the processing, has become cheaper, and then there were more open source systems, and then cloud came into the system. There are now virtualization, and eventually a lot more things have started to disaggregate. So these are just some of the different companies relating to the disaggregation of the hardware and software. So meaning that they no longer some devices no longer have to function only a specific task. They may be installed on commercial off-the-shelf devices. Okay. So now, since we mentioned that there is a disaggregation of also in RAN, let's look at the typical RAN setups and see how they differ from the Open RAN. Okay, so in the traditional RAN, there are base stations like this, maybe in 2G and early 3G. Both the baseband unit and the radio unit are co-located. So meaning the baseband unit, for example, if you have seen a base station like this, they have the cabinets here. Inside are different the different components for the purpose of signal processing, um, or other pre-processing tasks here. And then the radio unit in charge of the usually the analog and digital conversion. They're still here, and you have to run through the long radio frequency cables before it is radiated by the antenna. Okay, so the problem with this setup is that this is usually there are more signal losses along here, and if the signal is lost somewhere here or degraded or attenuated, then of course it will affect the signal being broadcasted or being radiated, and also the distance that can cover the signal that can cover. And in later phases of 3G and in rollout of 4G, the radio unit is now nearer the antenna. So in this case, no, it's now nearer the antenna to minimize the signal losses because of the lengthy cables. And now, because they are separated, we now have the BBU, here BBU, and the remote radio unit, or sometimes called as remote radio head. So this part focuses on the RF side. This one focuses on the signal processing side. Yeah. And aside from the separation of the two, there is an interface that was introduced, this Common Public Radio Interface, or the CPRI. And then what else? There was a change as well. In the past, there were some copper cables in the RF cabling, and then this one is now it may be the fiber based cables. Okay, so that's the traditional RAN setup. And this is just another way of looking at it for the non-split architecture and the split architecture. So when you say non-split architecture, no, they have the baseband unit and the R unit in the same part, no, same cabinet. But in the split architecture, the RRU is nearer the antenna, and the baseband unit can also handle or can also serve a lot of radio units. So it would be more cost effective not to deploy. Okay, so also one thing to or important thing to note in traditional RAN is all the devices here, the hardware components of the baseband unit, the hardware components of the remote radio unit, the interface, the front haul interface connecting them, they are all proprietary devices, which means that if you purchase this from a vendor, then you need to purchase all the other components from the same vendor. So if this is from vendor A, then you should also buy RRU from vendor A and the CPRI from vendor A. So everything must be from vendor A. So if you have to change one component, then you have to upgrade from the same vendor. So that is that cost like a vendor lock-in, wherein the operators, they were limited to just buying from the single vendor. So that's for the traditional RAN or classical RAN, or also known as distributed RAN. Yeah, of course, this is the RAN, and then this RAN is connected to the core network. Okay, and there were some moves to make it more efficient and more somehow less traditional, wherein we have the centralized RAN, or also known as the cloud RAN. The baseband unit, which was in charge of the signal processing, is now no longer on the same site as the antennas. They may be located in the central office, and they may handle a lot of different remote radio units, very handled by the optical distribution network. So the remote radio unit may be replaced by active antennas and things like that. And the front haul interface is somewhat serviced by an optical distribution network. So it may be like kilometers away and so on. And the baseband unit here, some of them may be more on pulled together to manage a lot of different remote radio units. And so this is called centralized RAN, or sometimes cloud RAN. So it's not really on the cloud itself, but rather in a farther central office. And then there is also another technology like the virtualized RAN, or known as virtual RAN or vRAN. In this case, the baseband units are also maybe hosted far from the remote radio unit or from the antennas, and they are virtualized. So notice it's VBBU. They are virtualized and maybe running on top of the COTS servers. So if you need to upgrade your BBU, you just need to maybe like install a new virtual function, and you don't need to buy really a new set of hardware, unless of course the hardware no longer can accommodate the requirements in terms of the RAM, the storage, the processing power. Okay. So vRAN somehow transforms the RAN from a hardware specific RAN to like more on software based RAN. So is this ORAN already or Open RAN already? No, not yet. Because even though the baseband units are running virtually on the COT server, the problem is that the interface, the one connecting the baseband unit to the remote radio unit, is still proprietary. So if there are changes, you still need to, yeah, buy from the same vendor. Yeah. So this is just another way of looking at the different types of RAN. So we have the DRAN here, the distributed RAN, the traditional RAN, and everything is on the same cabinet or same device. No? Then Cloud RAN here, there may be different baseband units, and then the VRAN, you may have virtualized functions, and then for ORAN, it's almost similar, but the interfaces and the hardware are all open, not no longer proprietary. Okay, so this is also another way of looking at the evolution. We have the traditional RAN. It may be non-split or split. It depends on where the baseband units are located relative to the remote radio unit. And we have the centralized RAN. There are also two options here. If you don't split the BBU, or there's a split BBU, the BBU can be split into distributed unit and centralized unit. Okay, so what's the difference? Much later, we'll be able to cover what is the difference between the distributed unit and centralized unit. They just have different functions according to the protocol stack of the RAN. So they just serve different functions. And then the virtualized RAN is somehow they're running on cloud, not really the cloud, but maybe on the central office. And then later we have the Open RAN. In this case, the hardware are COTS based, a commercial off the shelf, like the RU, the BBU, and then the functions may not be virtualized. And the front haul, again, the front haul connects the baseband unit and the remote radio unit. And this is also an open interface. Okay, so other details we'll cover a bit later. Yeah. And then to summarize again, the different architecture, notice in the traditional RAN, all the different components, the hardware, the software, and the front haul interface, they are proprietary. So it's vendor dependent. So if you buy from one, you need to buy all from the same vendor. Eventually, the centralized RAN introduced the concept of pooling and distribution network, which made it slowly, towards virtualization and open RAN. And then virtualized RAN, wherein the baseband functions may now run on commercial off-the-shelf server, but some components are still proprietary. And then eventually for Open RAN, this is the goal of Open RAN. Although some in Philippines, we still do not have a deployed Open RAN scenario. There are already proof of concepts, but it's not yet deployed in the actual operating network of the telcos. Okay, but the goal is all the parts are, except the software side now, all the hardware will be open. Okay, which means if you need to change some components, or if you need to, if the operator needs to expand their coverage in other areas that do not have coverage yet, they don't need to rely on a specific vendor and specific model, but rather they can just look at the specifications needed and then purchase the more commercially available devices. Okay, but the software is proprietary, so that's why a lot of the vendors are moving towards software and AI and more on the virtualization, because there's a need to prepare your own software, although there are already available. But maybe this is where they can be ahead, no, in the competition, no, in the competition in the market. Okay, so this made it such that there will be more chances to expand their coverage. Okay, so the idea of Open RAN is that it will have virtualization. It will be based on open source and open standard. And later I'll discuss briefly the functional split. because you have different components in your baseband units and the remote radio units. Which component will perform certain functions? Will the baseband unit focus on just the MAC layer or something like that? And there's just a bit of a challenge in terms of interoperability. If the vendors do not follow the standards set by ORAN Alliance, there may be some issues in terms of interoperability. So there are also additional tasks to check whether different vendor um, hardware can interoperate and function as a whole radio access network. Okay, so now that we are already familiar with the evolution of ORAN, which is very significant because we need to understand why there was a need to make it open. It's mostly to allow from the perspective of the from the financial perspective, it will really boost the it will reduce the capital expenditures, and if the cost of deploying a new node is cheaper, then there will be more incentive to expand to different geographical locations. So that's the financial aspect. And then the next aspect is on the market side. If the operator is not like fixed, no, or not locked to a certain vendor, they can find other vendors, and then this will foster competition in the telco sphere. Okay. And then ultimately the users will benefit because if there will be more coverage, then they will experience more quality of service. Okay, so now let's look at the architecture itself. So just an overview again of the RAN components. We already have learned about the core, the transport, and the access networks. And our main focus really is on the access networks. And the main RAN components are the radio unit or the remote radio unit, or RU, nearest the antenna, and the baseband unit. Mostly more on the signal processing end, but later we'll be able to see more on the detail or the protocols under this baseband unit. Okay, connecting the baseband unit and the remote radio unit is the front haul interface. And the baseband unit to the core is the backhaul interface, or also the transport network. Okay, and this is just another way of viewing this. Now we have the core network again, the transport network, and then the access network. Okay, so in the access network or the radio access network, we have the antenna, which is the one providing the coverage to the user equipment or the mobile devices. The antenna connects to the remote radio unit, and then the remote radio unit connects to the baseband unit. So this is just one device that is this one remote radio unit device. Okay, and then there is a front haul interface here. And then there was some move to disaggregate the components of the baseband unit. It can be further split into the distributed unit and the centralized unit. And because they may be separated in terms of location, there is a need to connect them by an interface called the mid-haul. So again, we have the front haul, the mid-haul, and then the back haul. Each interface connects other components of the whole telecommunications system. Okay, so just to give you also an idea, when we say backhaul, it may be wired or wireless connections. Like there may be some satellite connections here, microwave access, or even some wired connections. Okay, and then this is just one way to look at the ORAN architecture. So if we relate it back to the previous slide, we notice you have your RRU, the DU, and the CU. If you look at it here, this is the RAN, this part. This is the centralized unit, the CU. and then this is the distributed unit, and then the radio unit. Just look at these three parts. Okay, we just introduce other new components in terms of Open RAN. They have just now have a O here, so to indicate that it's an O-RAN distributed unit. And then this is O-RAN radio unit. And then this is Open Front Hall. And then this is Open Centralized Unit. And then there are other components here, like the SMO. This was asked during the Kahoot. We have the system management and orchestration. More on it's responsible for the main management. It can connect to a lot of different nodes, not just a single node. There may be different nodes, maybe for G node B, E node Bs, or the 4G nodes and the 5G nodes. And then there's also this near real-time RIC. This one is it supports tasks that require less than 1 second of latency. So actually, we'll discuss more on the near real-time RIC in the next webinar, but later I'll discuss just a brief overview of this one. Okay, so they're also interconnected by different interfaces here, which we'll be able to cover a bit later. What you need to understand on this slide is we have the RAN, and then for Open RAN, they're usually just called ODU, ORU, OCU. And these different RAN may be connected to the near real-time RIC so that the RIC can gather intelligence, can gather data, how the RAN is operating, how the RAN is functioning. If it can gather data, then later it can try to optimize the network. Maybe if it is expecting that there will be some handovers, maybe if it is expecting some sort of network optimization traffic and things like that, then it can provide some intelligence to the radio access network. Okay, so in the past, without this RIC, they just have to process the data and then send it out. But this one, there will be some feedback, some sort of closed loop feedback back to the intelligent controller. And then this one will try to optimize the network. Okay, so how it will optimize, it will be, there are some moves to create some software, usually proprietary software on the RAN intelligent controller. Okay, so this is what I'm showing here is somewhat similar as well in this diagram, but I'm trying to slowly go into the ORAN architecture. Notice that the colors are, I hope the colors are obvious now. We have the SMO, violet, then yellow, orange, and red. So if we go to a different way of viewing the ORAN architecture, we still use the same color so that it's easier to understand. So you still have your RAN components here. We have the distributed unit, the radio unit, and the centralized unit. And then this one consists, or composed one node. There may be other nodes as well that have different CU, DU, and RU as well. And then the near real-time RIC here, and then the service management and orchestration, which also contains another type of RIC, which is the non-real-time RIC. So near real-time, because it's almost real-time, it's less than 1 second. Mostly tasks that requires 1 second of latency. Mostly anything that requires immediate decisions or immediate application. But for non-real-time RIC, it supports tasks greater than 1 second of latency. So anything that maybe requires some modeling, maybe it requires some machine learning or AI component, mostly more likely it will be on the non-real-time RIC. So it's easier to understand because non and near real-time, the near real-time is the one that's quite fast, less than 1 second. Okay, so there's also here an O cloud because this different components may be connected to the cloud, wherein the cloud can just get some data because if it gathers a lot of data, then there will be a huge amount of data that must be processed later on. Okay, so this is actually the ORAN architecture. I hope that you were able to see the components. Just look at this part, the orange and the red blocks. This is the RAN, and it's considered open RAN because yeah, the components are open in the sense that they don't rely on specific hardware to operate. They may be virtualized on top of the physical commercial off-the-shelf device. And there are a lot of interconnections here. So we can maybe start first with the front hall interface. Remember, a front hall interface connects the distributed unit and the radio unit. Now, if you go back to the slide before, connecting the remote radio unit and the distributed unit, that is the front hall interface. Again, the radio unit connects to the antenna. So it's the one connecting to the user side. Okay, and we have the open front hall here. No, there's just a plane here, like this is for the management plane, and then the control and user plane. But essentially, anything connecting the DU and RU is the front hall interface. Okay, what else? We also have the DU and the CU. This is the base. This is originally just the baseband unit. No? So connecting the two is the mid-hall interface. In this case, it is F1. And then notice this is the near real-time RIC. The near real-time RIC connects to the different nodes. Like for example, this is one node, one ORAN, one E node, B node. Then there may be others like this color green. Maybe if you zoom in, I mean, this is just a representation, but if you go into this E node B, there are also CU and DU and RU here. There may be another E node B somewhere else. Not limited to just two, depending on the deployment of the telco operator. So the new real-time RIC connects to these nodes via the E2 interface. So the E2 interface, because the new real-time RIC should be able to gather data from the different nodes so that it knows whether the RAN is operating efficiently or whether there's a need to maybe what do you call that, upgrade, no? Maybe they notice that, oh, this type of device is currently overutilized, so maybe we can look into this and see if we improve or upgrade and add more virtualized function, would it perform better or something like that, you know? Okay, and then connecting the two RICs are is A1 interface. Then the SMO is on top now. There's also here an O1 interface. O1 connects the SMO to the nodes. This to the E node B. And well, this is also E node B because this CU, DU, and RU are part of the nodes. That's why O1 here is also connected to the other components. Okay, what else? We missed O2. O2 interface is towards the cloud. Okay. So if there's a need to maybe store the data or further process it or maybe share other details, they can connect to the cloud. Okay. What is also important here, in this ORAN architecture, there are interfaces that are defined by 3GPP, the third generation partnership project. This is the organization in charge of the management, maybe standardization of the cellular network technologies. So they already defined this mid-haul interface here, and even the E1 interface, connecting the control plane and user plane, and the X2 interface, connecting to the other components. Okay, but the ORAN specified interfaces are usually those connecting to the RIC. Notice the E2 interface because this one is introduced in the ORAN architecture. That's why it's color green in this case. So if you're going to be asked later in Kahoot, you just revisit the architecture. Okay, which one is connecting to the RIC? Because I know the RIC is an ORAN defined component. If it is connected to the RIC, then it is ORAN specified. So later, I hope that you can answer that in the Kahoot questions. I think it was asked the E2 the FH, and I think O1 no, isa. So there were three answers na in that question. Okay, so um, if you want to see this, no, you can visit this slide, this website, docs.o-ran.sc.org, and then look for the architecture. No? Usually it looks like this. No? We just also introduce some colors so that it's easier to discern compared to the other diagrams. Yeah, so this is actually the heart no, of this lecture. So I hope you were able to grasp no, the different parts. And in the next slides, no, since we still have time, we'll look into further details on this. Okay. Yes. In some cases, and sometimes they use this ORAN Alliance reference architecture. But don't worry, if you look at this, you'll notice that it's still the same. No? It still has the DU, the RU, and again, when you connect the two, it's the front hall. And then we have the CU again, centralized unit, connecting to the DU. And again, what is F1? This is the mid-hall interface. So front hall, mid-hall. No? And then it just mentions it is multi-RAT or multi-radio access technology, which means no, it can handle like multiple cellular technologies, maybe 4G, 5G. And then the near real-time RIC connects to the different RAN components to gather the data. And then the near real-time RIC connects to the non-real-time RIC. So pag sinabing near real-time, when you say near real-time, it's supports tasks that would be less than 1 second of latency or 1 second of delay. And for non-real-time RIC, usually this one is for greater than 1 second of latency. We'll cover more on this in the next webinar session. Okay, and actually in their architecture, they have further details. But if you compare it to the previous one, it's the same but more specific this time. There are more details in terms of the different parts, the SMO, the management orchestration. They have this different parts like mostly they focus on the policies, what will be the network policy configuration, and also in the near real-time RIC, they have different applications on it, running on it, maybe focus on radio management, quality of service, interference, mobility management. And here, there are just mentions of the different protocols, which we're not going to cover today. And notice that the DU and RU, they have certain functions as well, because the DU and RU have different network functions. Mostly RU is focused on the radio frequency side, and then DU is focused mostly on the signal processing side. Yes. So if you see, maybe if you're searching later, you notice that this is a different architecture. So actually, it's the same. It's just laid out a bit differently, but the components are still there. The nodes, the components, the interfaces are still there. This is just another way to represent the ORAN architecture. Yes. Okay, so I think I still have time. So we look at the different working groups. So I believe this was also mentioned before and also asked during the Kahoot session. We have the different working groups of ORAN Alliance. So there are 11 as of now. And if you look at the first 5, the first working group just focuses on the use cases and overall architecture. This working group is a team that looks into the overall responsibility of the ORAN architecture. They look at the task that needs to be completed in terms of the architecture, the scope of the architecture, and also maybe some tasks to drive other working groups like working group 2 and onwards. Okay, for working group 2, they focus on the non-real-time RIC. Again, when you hear non and near, just remember the 1 second. If it's near real time, then it's less than 1 second, and non-real time is greater than 1 second. Okay, and then since remember A1 interface connects the non-real time RIC and near real-time RIC. It's still part of the working group 2. So working group 2 supports non-real-time intelligent radio resource management, usually for optimization of higher layer procedure, policy optimization, and if there's a need for AI and ML models to be provided to the near real-time right now. So that's why in our previous webinars conducted by Ayora, there are also discussions on AI and machine learning. It's because we can already introduce these concepts or these models into the RAN or particularly into the RAN intelligent controller. Okay, working group 3 is more on near real-time RIC and the E2 interfaces. If you can recall, the E2 interface is the interface or the connection between the near real-time RIC and all the other RAN components. So looking back, it looks like it has a lot of connections, but you just need to take note that near real-time RIC connects to the node. And what are the parts of the node? You have the CU, the DU. Okay, so that's it. No, you don't need to really look in. You need to memorize, but you just need to remember. Near real-time RIC is connected to the node, no? And remember the types of nodes. Okay, so the E2 interface connects the near real-time RIC and the RAN. So this would enable the control and optimization of the RAN elements and resources, and of course collect the data and perform actions on the different components. Okay, working group 4, open front hall interfaces. The goal is to provide a truly open front hall interface for multi-vendor DU and RRU interoperability. So when I say front hall interface, this connects the DU and RRU. And if you have different DU and RRU vendors, then they should be able to interoperate. So they look into whether testing this one would allow the operation to go the same way as if it's the same vendor. And then working group 5, a lot more other interfaces. And the goal is to set up to ensure that the specifications would be compliant with 3GPP and should be also interoperable with different vendors. And other working groups here, not as significant in terms of our particular lecture today. We have working group 6, more on the cloud components. Working group 7, white box hardware. Working group 8, software architecture. Working group 9, open transport. Working group 10, operations and maintenance. And working group 11 is more on security. Okay, and this is again the slide showing the different RAN components. And let's look at the RAN architecture overall compared to the 5G or compared to the 5G. Okay, so this is how you look at the 5G network. We have the 5G core and then the RAN here, or the next generation RAN. There are some G node Bs here. And then the G node Bs and E node Bs are interconnected by the different interfaces like the XN interface. Okay, so the NG E node B is mostly for the non-standalone, and then the G node B is for the standalone. Okay, so previously we also mentioned that there are RRU and BBU, which is connected by the baseband, by the front hall interface, right? And then later there was a split between within the baseband unit. We had the CU here and the DU here, which introduced the mid hall interface. So this part, this three here, the CU, DU, and RU, they compose the radio access network, and they have some interfaces in between them. Okay, so why was there a need to split these parts? The main reason is that so the vendors, or rather the operators, may have more flexibility in terms of operating which functions is assigned to certain parts. Since everything may be virtualized, then they can just select now which functions may be assigned to the DU, which functions will be assigned to the CU, and so on. Okay. So what is functional split? Different protocols, different functions will reside in any of the three components. And depending on the split implementation, there may be more specific to certain deployment scenarios and things like that. It's really more on optimizing what you already have and to ensure that it fits to your use case. Because other operators may have different use cases. Maybe in certain areas, it would require there may be more end users in that area, or maybe they have less end users in that area, but it is far away from the main office or things like that. Okay, so what happened is that originally we have a monolithic RAN, the RU and BBU. The BBU may be split now because it was defined in the 3GPP standard, 3GPP technical report 38.801. Yeah, but I will not go into detail on that. But the main idea of that is to separate the centralized unit and the distributed unit, and the introduction of the mid-haul interface here. So the originally monolithic RAN is now composed of three different components. And you can split different functions based on whether it's a low layer split. When I say low layer, it's at the bottom part. So you're splitting just the RU and the DU plus CU. And then the higher layer split, you have the CU and then the DU RU. So actually, we'll cover more on this as well in the next webinar, since I'll also be handling the next webinar series. But I was just giving some overall discussion on this. Okay, so how ORAN complements 3GPP and other standards. We already know that some components of the architecture is defined by 3GPP. Some are like, for example, the mid-haul interface. It's defined by 3GPP. It was specified as gray in the ORAN architecture. And then we have introduced in ORAN Alliance or in ORAN architecture, there are now open components. Notice DU to ODU, RU to ORU. And then we also introduced the open front haul, and then the E2 interfaces connecting the near real-time RIC to the RAN components. And then the RAN functions usually is on the first three layers of the OSI model. For our engineers, you're quite familiar with this, but maybe we have student participants. If you're ECE, more likely this will be covered. We have different layers of the OSI models, and the RAN functions often work on the first three layers. And in each layer, there are different protocols. Of course, there should be protocols to ensure that each component follows the same standard and to ensure interoperable devices. Okay, so I will not go into detail on this. So maybe I can go to the certain parts to end since it's almost time. Okay. Just a minute now. Okay, so maybe I can go to this part, the implementation options and deployment scenarios. So I mentioned earlier that there will be different use cases depending on the needs of the mobile operators. And for example, maybe they have this like traditional deployment setup, wherein they have the core, the transport, and the RAN. If they are just using proprietary devices, then their software platforms and hardware are all proprietary. So if they need to change one, maybe if they need to change one device here, one hardware here, they should again buy from the same vendor. So that's what they call a vendor lock-in, lock as in lock, LOCK. But for an Open RAN deployment, maybe they still have the core, transport, and then the RAN. Okay, so the software, maybe the software side, maybe this one, maybe from vendor V2 running on the commercial off-the-shelf servers. And then maybe they have Open RAN hardware from different vendors, A, B, and C. If later they want to change maybe just one component here, maybe like this C, they can buy another one from a different vendor or maybe same vendor, but yeah, they're not limited to a certain vendor. Or if they need to upgrade their servers, they can just buy commercial off-the-shelf servers. So not specific to a certain vendor. Okay, so the service provider or mobile network operator can replace the Open RAN hardware and software, but of course they need to check whether it's interoperable, if they were able to follow the same standard and were able to communicate correctly. And due to open interfaces, the hardware from any vendor can be swapped and still work for software of other vendors. Okay, the same goes for if you have 5G Open RAN deployment. So just you can just mix and match depending on the need. You can have, for example, Open RAN CU or OCU here, and then ODU here, and then ORU here. So you can just mix and match depending on maybe you're buying from vendor one or vendor two. Okay. And then actually because of the virtualization, there aside from allowing Open RAN to be available for 4G and 5G, there were already some moves to allow to use the virtualized functions for the earlier generations. Like for example, for 2G, for 3G, they were able to virtualize these components and just run them on the typical baseband unit, which makes it good because this would allow the mobile operator to offer all the different generations and without buying the separate hardware. Remember, in the different cellular networks, they have different RAN components, different RAN names. So they have to buy in the past different components. If they want to upgrade to next generation, they have another set of components. But because of this, because of the virtualization and open systems, open source software, it would be easier to integrate all of them in the same commercial off-the-shelf hardware. Okay, so maybe to summarize, because I think it's almost time. Sorry, I think I exceeded a bit. No? So the radio access networks consists of the radio and baseband units, and there are different names for each generation. And the RAN architecture has evolved from the traditional setup to a more disaggregated setup. There were some virtualized RAN in that case, not in the virtualized RAN. Some components are running on top of the commercial off-the-shelf server. There is a centralized RAN wherein the baseband unit is pooled in a more centralized location to handle a lot of the processes. But eventually there is Open RAN wherein the components, the hardware interfaces are open. Now, it's not specific to a certain vendor. The proprietary aspect may be the software side. So that's where the competition is going to be more focused. But on the hardware aspect, everything should be open and interoperable. In Open RAN, there were main functional components. We had the DU, CU, distributed unit, centralized unit, and of course the radio unit. And we have the RAN intelligent controller, the RICs. There were two, near and non-real-time RIC. So when I say near, it's less than 1 second, or rather the task that it performs is less than 1 second, while the non-real-time RIC is for greater than 1 second. Okay, and then other essential interfaces, there were a lot of them. But remember, front haul is from RU to DU, mid haul is from DU to CU, and all the other components. A1 is focused on connection between the two RICs, and then the E2 interface, another important interface, connects the near real-time RIC to the other components. Okay, so I hope that with this webinar, even though it's really highly theoretical because we're focusing on the architecture itself, I hope that you were able to grasp the main idea of the ORAN, specifically the different important components of the architecture.